So that's it. That's how the test 4 will work. And move on. All right. Last class period, we were dealing with matrices at the end. We added and subtracted matrices, and then at the very end, we were multiplying matrices. Okay? Remember how we multiply matrices? We take rows of the first matrix and multiply them times the columns of the second matrix. And when we do that, we'll multiply we take this row, I think of it as turning upright, multiplying by the column, corresponding entries, adding those together. And if we did row 1, column 1, then we'd be in row 1, column 1 entry of the resulting matrix. If we were in row 1, column 2, if we multiplied row 1 times column 2, we'd be in the 1, 2 entry of the resulting matrix. If we did row 2, column 1, we'd be in the 2, 1 entry of the resulting matrix. And same thing, row 2, column 2 would be in the 2, 2 entry of the resulting matrix. So that's the one we did last time. And we ended up getting that result. Okay. Now we're going to continue doing some matrix multiplication to start with today. We're going to take these two matrices and we're going to multiply them. 3, 5, 1, negative 2. Multiply that times matrix 8, 4, negative 4, negative 6. And then we're going to multiply in the reverse order. 8, 4, negative 4, negative 6 times 3, 5, 1, negative 2. Now, I'm going to do this operation or do these operations. I'll just do them on the board by hand. So we're going to take 3, 5, and we're going to multiply it times 8, negative 4. 3 times 8 plus 5 times negative 4. Then I take 3, 5, multiply that times 4, negative 6. 3 times 4 plus 5 times negative 6. That's about spacing. By the way, when I take 3 times 8 plus 5 times negative 4, we can do that on our calculator if we want. That's 24 minus 20 is 4, I believe. Then we get 12 minus 30. That's a negative 18. Then we take the next row times that column. 1 times 8 minus 2 times negative 4. That's 8 plus 8, which is 16. And then 1 times 4 plus negative 2 or minus 2 times negative 6. 4 plus 12 is also 16. Right, that process. Let's try this process. 8, 4 times 3, 1. So 8 times 3 plus 4 times 1. 8, 4 times 5, negative 2. That's 8 times 5 plus 4 times negative 2. Negative 4. Negative 6 times 3, 1. Negative 4 is going to be multiplied times 3 minus 6 times 1. Then negative 4 times 5 minus 6 times negative 2. In this case, notice what we get. First entry is going to be 24 plus 4, that's 8. 28, excuse me. 8 times 5 is 40, minus 8 is 32. We get negative 12 minus 6, that's a negative 18. This is negative 20 plus 12. That's a negative. What everyone else got, by the way? I did that in my head. Now, here's the obvious thing we're pointing out here. Not just the process of multiplication of two matrices, but also notice that when I multiply matrix, if I call this A times B, it gave me a different answer when I did B times A. So the order of matrix multiplication is important. If you multiply A times B, where A is on the left, and then multiply B times A, where A is on the right, you get different results. Okay. Now, that is not true with addition. With addition, if we can add two matrices together, A plus B is the same thing as B plus A. So addition was commutative, what we saw last time. But matrix multiplication is not commutative in general. Okay, there's going to be special cases where it is, but like when we have the matrix with all zeros. But in general, matrix multiplication is not commutative. If I have A on the left times B on the right, that's not the same thing as B on the left times A on the right. Okay. So we have to be very careful about that. We have to be very careful when you multiply matrices that you do it in the right order. Okay. Now, here's the other weird thing about matrix multiplication, and we'll demonstrate with these two examples. We're going to take 2, negative 1, 1, 5 as a 2 by 2 matrix. So negative 2, negative 1, positive 1, positive 5. And multiply it times the matrix where row 1 is 2, 4, 3, and row 2 is negative 7, negative 2, 0. And then what would happen if we switch the order? I put 2, 4, 3, -7, -2, 0 on the left, and then put -2, -1, 1, 5 on the right. We'll get. I think that's the point you're gonna make. I bet. Yeah. That's so. You know how we took rows, turned them vertically, and then multiplied by columns? Well, even though we don't have the same number of columns in this matrix as this matrix, when I take this row and turn it vertically, it will match up with entries in that column. Does that make sense? So I can multiply this matrix by this one. I take -2, -1 times 2, -7. Let me just write that down. Actually, let me do this in my head. Is that right? So -2 times 2 is -4. -1 times -7 is going to be a +7. 4, that's going to be -4 plus 7 is a 3. That's tough, but we can do it. You understand what I'm doing there? I'm trying to do that in my head. You do it on your calculator too, if you want. -2 times 4, -1 times -2. That's going to be -8 plus 2. -6. This last one's nice because it has a 0. -2 times 3 -1 times 0. -2 times 3 is -6. Plus 0 is also -6. This one, we're going to get 2 minus 35. 1 times 2 is 2. 5 times -7 is -35. So I'm getting 2 minus 35 to -33. Then I'm getting 4 minus 10. -6 there. And then I get 3 plus 0. So I end up with that. Okay. So even while these two matrices weren't the exact same dimensions, I could multiply them because the number of entries in a row here match up with the number of entries in a column here. Right. Now on multiplying these two matrices in the other direction, if I try to take the 3 entries in a row in my first matrix and multiply times only 2 entries in a column of my second matrix, I'm missing an entry. Okay. So because the entries don't match up, like trying to do this, the number of entries don't match up in those 2 spots, or any of the spots, we say that we can't multiply. So this does not exist, right? Just like when we added 2 matrices, we said the dimensions have to match up perfectly if we want to add 2 matrices together. Otherwise, the sum of those two matrices doesn't exist. Well, if the number of entries in a row doesn't match the number of entries in a column, number of entries in a row in my first matrix doesn't match the number of entries in a column in my second matrix, then I can't multiply, and we say that does not exist. That product does not exist. But if the number of entries in a row does match up with the number of entries in a column, then it is going to exist. Now, I'm just going to write this down. I want you to note about the dimensions here. We had 2 rows and 2 columns in that first matrix. So it's 2 by 2. In the second matrix over here, it was 2 by 3. If you think about it, in order for us to be able to multiply these 2 dimensions have to match up in the middle dimensions. The number of columns in the first matrix, that's how many entries are in a row, times the number of rows in the second matrix, that's how many entries in a column. That makes sense? So these middle dimensions have to match up for this to work. And if we look at the dimensions here, this was 2 by 3 and 2 by 2. Since those middle entries didn't match up, I couldn't multiply. Is that right? Middle entries match up where the middle entries go. So if you're just looking at the dimensions, that's what happens. Now, here's another interesting fun fact. When they do match up, the resulting matrix size was the outside piece. Okay. Follow that? So when it does match up, the resulting matrix size is going to be the outside dimensions. So the inside dimensions have to match up. That's how we get to multiply rows times columns. And then the number of rows here and the number of columns over here is going to be our size of my matrix. And that's going to work in general. So the dimension behavior is that if we want to multiply matrices, number of columns in the first matrix, that's how many entries are in a row, has to match with the number of rows in the second matrix, that's how many entries are in a column. And so the first matrix, if it were m by n, if I could multiply, then the dimension of the second matrix are going to be n times something else. Let's call it p. So the middle entries have to match up. And when you do multiply, you're going to get a matrix of dimension m times p. That's what I was just, again, writing on the board. By the way, this means if I get to multiply matrix A times matrix B and get a result, and then I multiply B times A and also can get a result, that means all of those dimensions have to be, well, the square matrices, I should say, are nice to multiply. How about that? Well, I'll just say that. Square matrices are nice to multiply because all those numbers are going to be the same. All the dimensions are going to be the same. So if you want to multiply on the left, right, do any multiplication that we want, oftentimes we default to square matrices. Okay. I think I'll skip this one, this example. You can try this on your own if you'd like. But we have these two matrices. We've done a lot of 2 by something or others. Notice these are 3 by 3 by another 3 by 3. When I take first row times the first column, 2 times 8, negative 3 times 0, 1 times 7. What I'll get. That's going to take a minute. So I'll kind of skip that example. I do want to mention something about rules of mathematics with matrices. As we stated, when we're multiplying matrices, they are not commutative. So A times B is not the same thing as B times A in general. However, if we have a matrix and it's multiplied times the sum of 2 other matrices, and then I take that matrix and I multiply it by the individual matrices and then add those up. What do you think is going to happen? What would you anticipate from rules that we know of real numbers?
We just, I would say parentheses for n, what's in the parentheses, which then multiply with the result.
Yeah, yeah. So that's what I'm getting at. So the on this top one, we'd add first and then multiply. On the bottom one, we're multiplying individually and then add. Okay. If you think about this, these are 2 sides of the distributive property when we're talking about real numbers. If this is true, if these are equal in general, then we'll have a distributive property of matrices. Does that make sense? Now, this one example is not going to prove it, but I will show that this example does hold true, that you do get the same exact result either way. Okay, does that make sense? So let's do this. We're going to sum up in the first case. Before I multiply, when I add these two, I get 12, negative 1, 1, 6. And then I can multiply. This one's pretty straightforward to multiply. -1 times 12 plus 0 is -12. -1 times -1 is 1 plus 0 is 1. Okay, doing that. 1 times 1, 2 times 12, 1 is going to be 12 plus 2. That's 14. 1, 2 times -1, 6. It's going to be -1 plus 12, which is 11. If I do a multiplication here, -1, 0 times 7, 3 is -7 plus 0, so -7. -1, 0 times 0, 2. -1 times 0, 0. 0 times 2 is 0. Get 0. One, 2 times 7, 3. That's 7 plus 6. I'm sorry. 7. I said 7 plus 6. Wrote the wrong thing. And then 1, 2 times 0, 2. That's 0 plus 4. That's 4. When you do this one, we get -5 plus 0. Then we get a +1. Then we get 5 minus 4. That's 1. Then we get -1 plus 8, which is a 7. Notice what happens. We get -12, 1, 14, and then 11. Is that right? So what this is telling us is that even though commutativity does not hold up with matrix multiplication, other properties do. Other properties from the real numbers do. Addition, when we add two matrices, it is commutative. Turns out associativity also works. And this is one example that shows that distribution will hold. This doesn't guarantee, this one example doesn't guarantee that the distributive property holds, but I'm telling you it does hold. Okay. So the distributive property does hold with matrix multiplication. Okay. And like I said, so does commutativity of matrices. Now, the one thing I do want to mention is this. The distributive property does work. However, when I distribute the A, if the A starts on the left-hand side of the parentheses, then it needs to be on the left-hand side of B and on the left-hand side of C when I do the distributive property. Okay. If A were to have started on the right-hand side of the parentheses, then I need to put it on the right-hand side if I distribute it the other way. Okay. So A being on the left-hand side on the outside of that parentheses forces me to put it on the left-hand side when I do my 2 multiplications. So, and that's the same way with the associative property too. Phase on the left times the product of BC, then A on the left of B, product times C on the very right is also going to be the same thing. As long as I keep the A on the far left and the C on the far right. So associativity and the distributive property do work with matrix operations. Now let me do one other thing. I'm going to go back to example 7. I said I'm not going to do this. I kind of told the truth and kind of lied. I'm not going to do this by hand on the board. But I do want to show you how you can utilize your calculator to do matrix operations. Okay. It turns out there's a matrix menu in the calculator. And it's a good way to check that we've done things right. Okay. The matrix menu is this button, this inverse button after you hit the second. So you hit second and then the inverse. It's a little bit get a little bit of a glare there, but it says matrix right there. So I hit second and then that button. And this pulls up the matrix menu. We're going to use this in the next section as well. That's why I'm prepping it. Whenever you're dealing with a matrix, the first thing you're going to have to do is edit the matrix entries. I got to put the matrix in. So let's go to matrix A. Now, the 2 matrices that were on the slide were square dimensions, the square matrices of dimensions 3 by 3. Okay. That's what this top line is saying. What are the dimensions of the matrix you want? So I want matrix A to be a 3 by 3 matrix. And then you just type in the individual entries. You type in, let's say 8, and then enter, or you can hit 8 and then the right arrow. And then you type in the other entries. Oh, let's use matrix A as the 2, -3, 1. Is that okay? Sorry, I thought I was going to do the second one. Let's do A as 2, -3, 1, 0, 4, -6. That one. So my first entry should have been 2. My second entry will be -3. Third entry will be 1, and so on and so forth. Once you have that matrix all set up as matrix A in your calculator, then what you can do is you can either go back to the home screen or back to the matrix menu and put in this second matrix, matrix B, which is also 3 by 3. That's the one that started with an 8. So put in that second matrix in for B, 8, 0, -4, 0, -1, 2, 7, -9, 5. So I have matrix A is the left-hand side matrix, matrix B is the right-hand side matrix. If I want to multiply those, now all I have to do is go back to the home screen and then go into the matrix menu. Let me zoom out just a touch. So I'm going into the matrix menu. Now where it says names, I just hit enter for A. And then I put times back to the matrix menu and then enter B. So the names part brings them up to the home screen. And the edit allows you to change the entries. Here we're multiplying A times B. And notice that it does what you hope it does. You can also, if you wanted to, now that I have matrix A and B, you can actually add the two matrices as well, if you don't want to. Or you can multiply a matrix by a constant or scalar multiply a matrix, if I want. Right? I can do any of those operations that we've just done by hand on my calculator. Does that make sense? And that's always a good way to check that we've done it correctly, that we've done things correctly. By the way, just as a mental check that our calculator is doing the operation, you saw that when we multiplied the 1 entry was the number 23. That comes from 2 times 8 minus 3 times 0 plus 1 times 7. 2 times 8 is 16 plus 0 plus 7. 16 plus 7 plus 0 is 23. So it's a good check that our calculator is doing it right. And you can check the other numbers too. But there we go. Any questions about that? As a side note, what if I tried to multiply matrix A times another matrix which had dimensions 2 by 3? What's going to happen? Yeah, the dimensions aren't going to work up, at least not in this direction. If I took C times A, the dimensions would work. And if you try to do that, if you try to go 3 by 3 times 2 by 2, it's going to say there's a dimension mismatch on your calculator. And the same thing if you try to add them. If I tried to add those two matrices, it'll say, hey, the dimensions don't work out. They're not the exact same. So you can't do it. But like I said, if you did C times A, the dimensions are going to work out on that one. And whatever C was, I'm not exactly sure what matrix C was, but whatever it was times A, it was 2 by 3 times a 3 by 3. We got out of 2 by 3. Okay. So all of these operations that we did in this section can be confirmed or you can confirm in your calculator. Now, the next thing we're going to do with matrices is we're going to deal with Gaussian elimination. There is a mathematician whose last name is Gauss, very famous mathematician, and this is named after him. Okay. So that's the name of it. So here's the structure of what we're going to do. We're going to take a system of linear equations, like ones we were dealing with in sections 9.1 and 9.2, and we're going to turn that system into a matrix. Specifically, we're going to turn that into an augmented matrix. So what we do is we take our system of linear equations and I line up the x's, line up the y's, line up the equal signs, and line up the constants like I do when I'm using the elimination method. Okay. And furthermore, I make sure that my variable terms are on the left-hand side of the equal sign, and my constant terms are on the right-hand side of the equal sign. With an augmented matrix, we always want our constant terms on the right-hand side of the equal sign, our variable terms on the left. And then each row of the augmented matrix is just the coefficients of the variables, and then on the very right-hand side, the constants. Each column is going to represent coefficients of the same variable, x, y, or on the very right-hand column, the constant. Some people you'll see will draw a vertical line so that they know where the equal sign is. I typically don't, because I know the equal sign is always right before the constants, all right, in my head. So I typically don't draw that vertical line. Some people draw that vertical line in the augmented matrix. Some people don't. I tend not to. So if we have a system of linear equations like this, where it's already all lined up for me, it's pretty straightforward to turn that into an augmented matrix. Five, 10, 25 would be row 1. 7, 6, 3 would be row 2. And like I said, I tend not to draw the vertical line. You can if you like. But again, this is standing for 5x plus 10y is equal to 25. 7x plus 6y is equal to 3. Once we start getting bigger systems, a lot of times instead of using x's and y's, people will use x1s and x2s. All right. X1 just means first variable, X2 means second variable. The reason why we do that, especially is when we get really, really big systems, we run out of letters real quick. And so if you're dealing with things that have 6 variables, you go X, Y, Z, and then oh crap, what am I gonna use for my next letters? Maybe A, B, C, maybe you can use lots of different things. So people just start saying, you know what, that's just the first variable, we'll call that X1, second variable, we'll call that X2, third variable, we'll call that X3, and so on and so forth. It works the exact same way with subscripts on our variables rather than different letters for our variables. If I'm doing an augmented matrix, row 1 is going to be 1, -2, 10. Row 2 is going to be 3, 5, 8. Here's a system with 3 equations and 3 variables. I want you to think about what the augmented matrix would look like for this system of linear equations. And then write that down. Write down what the augmented matrix of this system would be. Everything is essentially lined up. There's only one thing I need to worry about here. Little wrinkle. So coefficient of x1 is a 1. Coefficient of x2 is a 5. Coefficient of x3 is a -9. Constant is a -17 in the first row. Second row, coefficient of x1 is a 2. What do I put as the coefficient of x2? 0. Yeah, just put the 0 entry. And then 1, -6. That's all. Last is 4, -6, 12, 2. And we're done. So now I have the augmented matrix for that system of 3 equations and 3 variables. Once we set up the augmented matrix, what we're going to do is we're going to do a process called Gaussian elimination. What we're going to do is we're going to create matrices that are equivalent in systems of linear equations to the augmented matrix, right? So if we have a system of linear equations, how can I create another system which is equivalent? Well, I can multiply one of my equations by a constant on both sides. In the matrix format, that means I can multiply a row by a constant number. Another way I can get the same system of linear equations is if I just swap the order of the equations. I put equation 1 first, equation 2 second, or equation 1 second, equation 2 first, I get same thing, right? Same solutions. And then the last tool is that I can replace one of my equations by a new equation where I take constants and add them up. In other words, I can add up the equations like I do in the elimination method after I've multiplied them by a constant. You guys remember the elimination method? Multiplied by a constant. That is our third tool. So we replace a row of our augmented matrix with 2 rows added together, all right? Possibly multiplied by constants. So all of those are going to create equivalent augmented matrices. Equivalent in the sense that the system of linear equations that they represent has the same solution. And then once we understand that Gaussian elimination gives us systems with the same solution, we say, let's use the easiest system that I can. Let's use the easiest form of the matrix that I can use with equivalent solutions. And that's called the row reduced echelon form of the matrix. Okay. Properties of the row reduced echelon form of the matrix say we have to use lots of zeros and ones. The lead non-zero entry of each row is going to be a 1. Those lead entries are called pivot positions. And below and above the pivot positions, we're going to force our matrix to have zeros below and above those pivot positions. And lastly, we'll have a stair-step effect with the pivot positions. So the first pivot position will be in the upper left corner, and then we'll go down and to the right and down and to the right to get to our next pivot positions. We'll always move down and to the right to get to our next pivot positions. Okay. This will make a little bit more sense when you see some examples. Here are 2 matrices that are in row reduced echelon form. These are the most common ways we're going to get row reduced echelon form, where we have like 1s on the diagonal, the main diagonal there, and zeros elsewhere. Except for my last column, which might have some numbers in it. Okay. These are the most common versions of row reduced echelon form. We have 1s on the diagonal, 0 elsewhere except for that last column. Notice that we have this stair-stepper effect where our lead entry in the upper left-hand corner is 1, then we go down and to the right to get to our next one, down and to the right to get to our next one. Now there are other versions of row reduced echelon form. Here are a couple of other versions. In this left example, we have a pivot position right here. If I move down and to the right, my second pivot position is actually down and 2 over to the right. By the way, you could have also had like a 4 right here instead of the 0. That doesn't have to be a 0. That could have been a 4 or whatever number you want. Okay. But that would also be a row reduced echelon form because we have 1 as the leading entry, zeros above and below those pivot positions. And then my pivot positions, to get to the next one, I go down and to the right. This is also over here. Row reduced echelon form, we have a 1. Then when you go down and to the right, you don't encounter any other pivot positions. There's only 1 pivot position in that whole matrix there. You'll notice in the bottom matrix, it's 3 by 4. We have 2 pivot positions. They are 1s. Zeros above and below the pivot positions. And we have this stair stepper effect where you go down and to the right, down and to the right. Okay. There's no pivot positions in this final row because it's all zeros. That work? So those are also row reduced echelon form. The key thing there is, again, where the pivot positions are, zeros above and below it, and we have the stair stepper effect down and to the right. Like I said, most of the matrices we're going to deal with, when we put them into row reduced echelon form, they're going to look like these two, one of those two. Okay, we're going to have 1s on the main diagonal and then zeros elsewhere except for the right-hand column. Okay. Here are a couple of matrices that are not in row reduced echelon form. This first one is not in row reduced echelon form because that 5 is in a pivot position, but it's not the number 1. Okay, I need to turn that 5 into a 1 to put that in the row reduced echelon form. This is not row reduced echelon form. I have the right pivot positions. I have the stair stepper effect, but I have a 2 above the pivot position, and we want that 2 to be a 0 for it to be in row reduced echelon form. Does that make sense? So these two are not in row reduced echelon form. That needs to be a 1. That would need to be a 0. So all we're going to do is use those Gaussian elimination tools to produce row reduced echelon form. Okay. I'll do this once by hand, but I'm only going to do it once by hand. Then I'll turn to my calculator and show you how to do it by calculator. But I do want to show that it is possible to do it by hand. So I'll use this matrix by hand and do Gaussian elimination just to show you kind of the process that it's going through. And then I'll turn back to the calculator and show you how to do it by calculator. That's much, much quicker. So we're going to use this matrix 2, -5, -28, 3, 1, 26. If I were doing this by hand, I'd say this 2 is in a pivot position. Let's start with that. I'm going to force it to be a 1. The way I force it to be a 1 is I multiply this entire row by a half. And then usually what we do is to say we're going to replace that. Whatever I get when I multiply that by a half, I'm going to re-put it in the first row again. Does that make sense? So that's going to turn into 1, negative 2.5, negative 14. And then this row, since we're not doing anything to it, stays the same. I only change one row at a time, usually, when I'm doing Gaussian elimination by hand. Only change one row at a time. Now, I want to force this 3 to be a 0. The way I do that is I'm going to do essentially the elimination method and replace this second row with negative 3 times the first row plus the second row. Hopefully that doesn't. So we're multiplying by a negative 3 on this first row, and then we're going to add it to the second row. Everybody okay with that? If I take negative 3 times 1 plus 3, I get a 0. So negative 3 times 1 plus 3 gives me a 0. Negative 3 times negative 2.5 plus 1, I believe that's a negative 6.5. Negative 3 times negative 14 plus 26, that's going to give me a bigger number. Negative 3 times negative 14 plus 26 gives me 68. Okay. I'm just confirming that's what we get. Everybody see how I got a 0 there? So this is the tool we use. And essentially what that is that's kind of an elimination step method. Okay. Wait, negative 3 times negative 2.5? Oh, that was negative 2.5. Shoot, I messed that up. That should be a positive 8.5. I apologize. Is that right? Negative 3 times negative 2.5 plus 1. Positive 8.5. And then positive 3 multiplication. Everybody right with that? Okay. Now, that just changed my second row. My first row is going to stay the same. It's going to stay 1, negative 2.5, negative 14. At this point, I can see where my second pivot position is going to be. At this point, my first pivot position has zeros above and below it. So now I move on to my second pivot position. I'm going to turn it into a 1 and then force zeros above and below it. Okay. So I'm going to multiply by 1 over 8.5 and just replace that second row with whatever I get by multiplying each entry by 1 over 8.5. The first row doesn't change right now. First row stays the same again. 0 times 1 over 8.5 is still 0. So that keeps that first column still nice. 8.5 divided by 8.5 is a 1. 68 divided by 8.5 is 8. So now I've made this second pivot position a 1. And I want to force a 0 above and below it. There's no below, so I only need a 0 above it. And so I'm going to do the same process that I did over here. I'm going to say, well, let's multiply this by a 2.5 and add it to the top row. So we're going to multiply by 2.5, add to the top row, and then I replace the top row only. By the way, if you do 2.5 times 0 plus 1, you just get a 1. 2.5 times 1 minus 2.5 is a 0, like what we wanted. And then 2.5 times 8 minus 14 is a 6. That second row would still be 0, 1, 8, and that is in row reduced echelon form. The shorthand for row reduced echelon form, see I've write all those those words, is just RREF. So that's now in RREF, and we've solved the problem that we were asked to solve. Okay. We were asked to put this in row reduced echelon form using Gaussian elimination. And so that's kind of how the process goes. You set out a first pivot position that's on the left-handmost side, upper left that you can. Make it a 1. And then force the numbers above it and below it. There's going to be no above in this case, but you force the numbers below it to be 0 by that elimination thing. Once you get one column with 1 and then zeros below it, then you move down to the right, set up your next pivot position, force it to be a 1, and then force zeros above and below it. And you can imagine if you have a really big matrix, like a 4x5 matrix, you could do this process over and over and over again. You'd have to make a lot of different zeros, take a long time, but it is just a process. And the nice thing about a process that's repeatable is that it's programmable, all right? And in your calculator, you can program a process like this, and it's already into your calculator, all right? So we're going to use your calculator from here on out. Now, before I get off of this example, think about what this would mean if this were a system of linear equations. If this were a system of linear equations, it's saying these equations that are represented here have the same solution as the equations that are represented here. And the equations that are represented there are just 1x plus 0y is equal to 6. And 0x plus y is equal to 8. In other words, when I force RREF, the solution to the system of linear equations is staring me right in the face over there. X is 6, y is 8. Okay. So when we force row reduced echelon form, as long as we have a nice row reduced echelon form like we do here, the solution is right there in the right-hand column, essentially. like I said, from here on out, if you want to do it by hand, you can. If you want to do row reduced echelon form and get row reduced echelon form by hand, you can. But we can do it fairly easily on our calculator as well. So I want you to put in this 2x3 matrix into your calculator. Just edit, I'm going to edit matrix A. It was a 3x3 matrix. I'm going to change it back to a 2x3 matrix with entries 8, 3, -2 in the first row, 4, 1, 2 in the second row. So there it is. Once you've put your matrix in, you go back to the home screen. I'll clear that out. The row reduced echelon form button is actually also in the matrix menu. But under the math. So this is the mathematical operations you can do with matrices. And if you scroll down far enough, what you'll see is an RREF. By the way, if you look at those last 4 entries, those are just doing Gaussian elimination one step at a time. So if you want to swap the rows of the matrix, you can. If you want to add rows up in a matrix, you can. If you want to multiply a row by a constant, you can. If you want to multiply a row and then add it to another row, you can do that too. So you can do those steps one by one. It's a lot easier than just to use RREF. And then go back into the matrix menu. My matrix was A. And there you go. Now I've put that matrix into row reduced echelon form. And if my variables were X and Y, I'd say X is 2, Y is -6. That would be the solution to that system of linear equations if this were an augmented matrix. Okay. And you can do it on bigger examples as well. I think I'll skip this example for right now because we'll do a bigger example in a second. But you can imagine this is a 3x4 matrix, and your calculator will put it into row reduced echelon form in a fraction of a second. So let's go back to the examples that we had earlier with the systems of linear equations we were dealing with. Okay, we've already written an augmented matrix for this system of linear equations. It was 5, 10, 25, 7, 6, 3. If I wanted to solve this using row reduced echelon form on my calculator, all I would have to do that was 2x3 augmented matrix. I still have it written on the board if you want to check that out. I didn't erase it. That's why I didn't erase it. So 5, 10, 25, 7, 6, 3. Go back to the home screen. Oh, excuse me. matrix. Sometimes it's easier to go up instead of down. Less. Row reduced echelon form. I'm using matrix A. There it is. I get the row reduced echelon form is 1, 0, -3, 0, 1, 4. Still left a little more room, I guess, but. So the solution to this system of linear equations is going to be when x is -3 and when y is 4. Or if we wanted to write it as an ordered pair, -3, 4. You can check that answer if you'd like. Plug in -3 into x and 4 into y in each equation. You'll end up showing that you actually get the same thing. Does that work? Try that with this one on your own. That's the next example, is this one. Take this system of linear equations. We've already made the augmented matrix. Put that augmented matrix into row reduced echelon form. See what you get. And then give the solution to the system. All right, I looked through it quickly around. Everybody seems like you got it. So 1, 0, 6, 0, 1, -2. And that would mean that the solution happens when x1 is equal to 6 and x2 is equal to -2. All right. Our variables are x1 and x2 this time rather than x and y. If you wanted to put that in an ordered pair, you could put 6, -2 as well. When you do subscripts in ordered pairs, you do them numerically. So x1, x2, x3, and so on. But so if you wanted to do an ordered pair, you can. All right. Now, what about the one we did earlier? That was 3 equations with 3 variables. I want you to try this example on your own. Again, I still have that written on the board over here on the right-hand side of the board. You know, reference. Try solving this system of linear equations on your own. Go to that man. First, go to your. Right. Now go back to your matrix. And section, and then all the way down to B. And now go back in the matrix menu. And put an A.
Oh, yeah, that's how I was just putting it in the bracket.
Yeah, that's right. Yeah, all right.
Thank you.
Now, this one, if you did this by hand, would take a long time. Both using Gaussian elimination and if you try to do this by hand using techniques we did when we were solving systems of linear equations. Okay, remember when we solved systems of linear equations, we had to like take two pairs and eliminate one of the variables. And then we got down to two equations, two variables, and then we eliminated another one. Then we got down to one equation with one variable. And then we had to go back and plug everything in. When you do row reduced echelon form, everything is just faster on your calculator, if you do it on your calculator. When I did this, I ended up with a row reduced echelon form that looks like this. -4, 1, 2 on the right-hand columns, and then my ones on the main diagonal everywhere else. So this means that x1 would have to be -4, x2 would have to be 1, and then x3 would have to be 2. Or if I put my solution as an ordered triple, again, we do it in subscript order. So it'd be -4, 1, 2. That's it. This is one of the faster ways to solve systems of linear equations. And once you have this method, then you could have gone back into sections 9.1 and 9.2 and solved all of those problems using this technique. Again, we have to make sure that we're lined up in the correct way. All of our x1s, all of our x2s, all of our x3s, then all of our constants. But if I have everything lined up in the correct way, I can let my calculator do all the hard work. Okay. So that's the advantage of using this technique. very easy to program. We have this nice program into our calculator, and there's a lot of other computer software that has programs that'll do RREF on a matrix. So it's a very fast method of solving systems of linear equations. Now, I do want to point out something that could happen. All right. Let's do the technique of finding the row-reduced echelon form of the augmented matrix representing this system of linear equations. Okay. So let's do RREF, or let's find a solution using that same technique. Okay. I'll write that down here. Most of it's similar. So we have x minus 3y is equal to 7. Negative 2x plus 6y is equal to negative 10. This is going to represent a 2 by 3 augmented matrix. We're going to have a 2 by 3 augmented matrix. The entries are going to be 1, negative 3, 7, and negative 2, 6, negative 10. I'll go back to the home screen. By the way, I've done RREF of A every time. If you do that every time over and over, if you don't want to go back to the matrix menu, you can just hit second enter. Now that you've changed your A, it'll do RREF of the new A, whatever it is. But second enter will get you there too. So when I do my row reduced echelon form, I do not get the nice ones on the diagonal that I've gotten so far. I get 1, negative 3, 0. And then 0, 0, 1. What's that mean for my solution? Well, here, this stood for 1, remember, x1, that's the coefficients. Coefficients of x1 are in the first column. Coefficients of x2 are in the second column. In this case, the coefficients of x's were in the first column. Coefficients of y were in the second column. Constants were in the third, and our equal sign was always right there. So this is telling you that 0x plus 0y is equal to 1. In other words, that's telling you 0 is equal to 1. Which is obviously not true. Okay. 0 is not the same thing as 1. I think it is. I'd trade you $0 for $1 anytime you like, right? So, since this is a false statement, what that is indicating is that this system of linear equations has no solution. Okay. So this is the no solution version of RREF. It's when we have all zeros and then a 1 in one of our lines. Okay. So if you ever have that in one of your lines, then it's a no solution. Now, I won't go through all the steps, but if you did if you replace the -10 with a -14, and then did the RREF of that, what you'd end up with is 1, -3, 7, and then a row of all zeros. Here, 0 is equal to 0, that's true, right? So what this is an indication of is that these two lines were actually the same line. Okay, so this is the infinitely many solutions case. That makes sense? This is saying x minus 3y is equal to 7 and 0 is equal to 0. So what can x be? X can be anything. What can y be? Well, y and x have to be in this relationship, but there's lots and lots of different pairs that will work. There's infinitely many solutions in this case. Okay. Is that all right? Infinite solutions. Most of the time, we're going to have our system turn out to be this, where we get a unique solution, like 6, -2. Or, we've done a lot of these where we have unique solutions. But this is the no solution example. This is the infinitely many solutions example. Those could arise as well. That's where we get those other weird will-reduce echelon forms. Okay. Questions about that? Pretty good. Oops. That was the next example, the -14. I forgot to say. I said I wasn't going to write all the steps, but that was the next example. Okay. Good. Well, that is Gaussian elimination. We use Gaussian elimination to put an augmented matrix into row-reduced echelon form. And that was a really nice way to solve a system of linear equations. And now you can do that not just with what we had today, but if you remember back in sections 9.1 and 9.2, we were doing, things like this, where we had two acid mixtures mixed together. And the way I did it when we went through this problem at the time was I just looked at where they crossed on Desmos. You guys remember that? If you wanted to, you could do this one very quickly after you have the equations with row-reduced echelon form. So I'll do this just for an example. we had acid mixture A and B, if you remember. The total equation was A plus B was equal to 210. And then the percentage equation was 0.14A plus 0.45B is equal to 22% of 210. Okay. That, right? Oh, I'm gonna project it on there. Okay. There you go. As an augmented matrix, that would be 2 by 3. A plus B is equal to 210. And then 0.14A plus 0.45B is equal to 0.22 times 210. By the way, and what's going to happen here in a second when I hit enter is that it's going to do the multiplication for me and write a 46.2 there. Okay. And if you remember last time, we said, oh yeah, they meet up at about 155.81 and then 54.19. Right, when we did this our first time going through this problem. If you want the exact fractions that those numbers are, you can actually on your calculator just hit the math key and then change all of the numbers into fractions if you'd like. So that's saying A as an exact fraction is 4830 divided by 31. I don't know what that is. I know it's about 155.81. And then B, if you were going in giving an exact answer, it'd be 1680 over 31. Again, that's about 54.19 millimeters. Okay. So that way you don't even have to use something like decimals on those problems. You can just plug them in your calculator and be good to go. And again, I like this method a lot better because then you don't have to adjust the window to see where things actually cross. If you had to do this on the graphing part of the calculator, you know, like in the y equals, then you'd have to adjust the window until you can see where they cross. And sometimes that takes a while. Sometimes that's not very fun. So. All right. Questions about that? Good. So all of those problems that we did earlier can be done through that Gaussian elimination. Good. Now, I'm going to cover one more section on matrices. I'll cover this pretty quickly. But it's an interesting topic. So The last section that we deal with matrices are on matrix inverses. Okay. Now, before we get to the concept of a matrix inverse, I'm going to start with the concept of an identity matrix. The identity matrix is a square matrix where the main diagonal is 1 and there are zeros elsewhere. You'll notice that in the nice row-reduced echelon form of the systems we were dealing with, we had essentially the identity matrix and then another column. All right. The reason, usually the identity matrix, by the way, is denoted with an I, sometimes with a subscript to show you the size. So I3 is the 3 by 3 identity matrix. A lot of times they won't write the subscripts though either. They'll just imply that it's the right size. So they just write the letter I. So identity matrix denoted as I, or I with a subscript. 1's on the diagonal, 0 everywhere else. The reason it's called the identity matrix is because if we multiply it by any square matrix, we're going to get that square matrix back. Think about the 2 by 2 identity matrix. What would happen if I multiplied 1, 0 times AC? I just get A. Then 1, 0 times BD, I just get B. 0, 1 times AC, I just get C. 0, 1 times BD, I get D. So notice that I get A, B, C, D back when I multiply on the left by the identity matrix. If I multiply on the right by the identity matrix, then AB times 1, 0 is A. AB times 0, 1 is B. CD times 1, 0 is C. CD times 0, 1 is D. So once again, I get the matrix back. So if I multiply on the left by the identity matrix or the right, I get the matrix back. That's why it's called the identity matrix, because it gives you that matrix back. Okay. So long as the dimensions are correct, identity matrix times any matrix A gives me back A. A times an identity matrix gives me back A. Right? So the identity matrix works. That's 1 times anything. It works like the number 1 in real numbers. Anytime you multiply 1 times a number, you get that number back. Right? Again, so long as I have the right dimensions, that I can actually do the multiplication, we're good to go. Once I know what the identity matrix is, then it makes sense to say, if I have a matrix, what can I multiply that matrix by to give me the identity? It's kind of like in real numbers. If I said, what do you multiply by 5 to get the number 1? You'd say it's 1/5. That's the multiplicative inverse of 5. So 1/5 times 5 becomes 1. So it's the multiplicative inverse of 5. That is 1/5 is the multiplicative inverse of 5. Okay. And we denote A to the -1 power as that matrix that when you multiply it times A, you get back the identity. We are also, in this class, going to require that both multiplications are going to work. Not only is A times A inverse going to give me back the identity, but also A inverse times A will give me back the identity. That means I'm going to force the A to be a square matrix in order to have an inverse. That's the traditional way of doing it, okay? So in order to have an inverse, A has to be a square matrix. Now there's a few ways to find inverse matrices. We'll probably primarily use the third method here. That's just find it on our calculator. But there's two other methods as well. One method would be to create a really big matrix that looks like the rows and columns of A on the left side, and then the identity matrix on the right-hand side, and put that into row-reduced echelon form. When you put it into row-reduced echelon form, that's going to force the diagonals. So it's going to force us to have the identity matrix on the left-hand side now, and the right-hand side will have kept track of those operations, and therefore the right-hand side will become A inverse. I'll show you that once quickly, but in the 2x2 case, there is a special formula for that. So in the 2x2 case, you can actually just use a formula to find the identity. You could do that in 3x3, but it would be a really messy formula. Okay, really, really messy formula. And then the easiest way is just use technology to say, hey, calculator, what's the inverse of this? And have it give it to me. Okay. Just so you know, the formula in the 2x2 case is that if A looks like the matrix A, B, C, D, then the inverse is 1 over this number AD minus BC. So that's scalar out front times D negative B negative CA. So we have a scalar times this matrix, where it kind of just swaps D and A and then puts a negative on B and a negative on C. We swap D and A, puts a negative on B, negative on C. So that's the special formula in the 2x2 case. So I'll find the inverse of this matrix. And I'll use all three ways of doing that to show you that they're all going to give you the same thing. Okay, so we have 5, 10, 7, 6. I'll call this option 1 because it was our first option that I listed, but this is not my primary go-to method on this. we write 5, 10, 7, 6, and then we add 2 more columns that look like the identity matrix. And then we row reduce echelon format. Okay, so I'll just turn to my calculator. This is a 2x4 matrix. I'll do an RREF of that. And what we get is 1, 0, 0, 1, and then negative 0.15, 0.25, 0.175, negative 0.125. So that's option 1. And this would have been my A inverse. Talk about that in a second. Okay. Option 2. A inverse 1 over AD minus BC times, again, I just swap the A and the D, and then negate the B and the C. Okay, where I'm thinking of this as A, B, C, D. So what that would be, I'd have the scalar 1 over 5 times 6 minus 7 times 10, or 10 times 7. I'll put a 6 here, a 5 here, negative 10 here, negative 7 there. By the way, this is 5 times 6 is 30, minus 70, that's a negative 40. Bear that. So this is 1 over negative 40 times 6, negative 10, negative 7, 5. And when you multiply 1 over negative 40 times 6, that's where you get the negative 0.15. 6 over 40 is 0.15. 6 over negative 40 is negative 0.15. Negative 10 over negative 40, that's where you get the 0.25, that's a quarter. This would be negative 7 over negative 40. That's 0.175. And then a 5 over negative 40 is a negative 0.125. Is that right? Just divide all these numbers by negative 40. So that's option 2. Option 3, again, this is the one that I use most often, is just use the inverse button on our calculator with matrices. Okay, so put in this matrix is matrix A. once you have that matrix in as matrix A, so oops, thought I had that on. Excuse me. So I have 5, 10, 7, 6. It's got to be square for this to work. Then all you have to do is say, let's take the inverse of that matrix. And the inverse button is x raised to the -1 on your calculator. Okay. And there you go. If you want, just like we did last time, you can write fractions. And notice those are the exact same fractions I was getting through the formula. Although here they're reduced. Like -6/40 reduces to -3/20. 7/40 doesn't reduce. But -10/-40, it's like a 4. So inverse button on our calculator can give us the inverse matrix. No, dang it. I don't have that. So you can do that for any matrix. You can plug in the inverse button on any matrix. Now, I do want you to be careful. The inverse button on matrices like 1, -2, 3, 5 is going to be fine. But I want you to see what's going to happen if we have a matrix like 1, -2, -4, 8. I'm going to put that into my matrix B, just so it's not in matrix A. Done that earlier. So there's my matrix B. If I go B inverse, it's going to say that there's a problem. It turns out B, this matrix that I just wrote, is a special type of matrix called a singular matrix. And singular matrices are ones that do not have an inverse. Now you can see that on your calculator it gives you an error, but you might say, why does it give me an error? What's wrong with matrix B?
Forming that the thing becomes like 1/0.
Exactly. That's what I was headed to. So if you think about this second option, it's kind of clear that this AD minus BC cannot be 0. If we had the matrix, oh shoot, I shouldn't erase that. That's fine. But what matrix was it? 1, -2, -4, 8.
1, -2, 3, 4.
8. AD would be 1 times 8. -4 times -2 is also 8. So we get 1/0 is our scalar that we'd have to multiply by. Okay. And anytime we have a 1/0, that's problems. That's undefined on the real numbers. And so that's where the problem's at. Okay. Notice that also, this is the special case where if you had an augmented matrix, let's just call this star star, something over there, and you tried to do row reduced echelon form, what would end up happening is you'd either get 0, 0, 1, 0 like that, or you'd end up getting some other number and a row of zeros. You'd end up getting the either no solution case or the all solutions case, or not infinitely many solutions case. Excuse me. That makes sense. So when we did option 1 and we row reduced it, it would not have turned into the identity matrix on the left-hand side, is what I'm trying to get at. We follow that? So when you row reduced it, you would not get the identity matrix on the left-hand side. You get something that looks like that. So now we have 3 ways to see that. And all that is to say that there are certain matrices, like this one, 1, -2, -4, 8, that do not have inverses. And like I said, those are called singular matrices. And it's like the number 0 doesn't have a multiplicative inverse. There's nothing you can multiply by 0 to get 1. These matrices are kind of like 0. They're not the number 0, but they don't have a multiplicative inverse. So the ones that don't have inverses are singular. All the ones that do have inverses are called non-singular. Now, I'm going to briefly just talk about matrix equations. Okay. And the relation to systems of linear equations. We're not going to deal with this a lot. I'm just going to show you what it is. I like the RREF system better to solve systems of linear equations using Gaussian elimination, RREF. But you can also use matrix inverses to solve systems of linear equations. A system of linear equations can be written as a matrix equation, where we have a matrix A, which is our coefficient matrix, times a matrix X, which is our variable matrix, times our matrix B, which is a constant matrix. And if you multiply this out, this means A11 times X plus A12 times Y is equal to B1. And then A21 times X, A22 times Y is equal to B2. That makes sense? So that gives you 2 linear equations in this matrix equation. Okay. If we want to solve a matrix equation that says A times X is equal to B, all we have to do is multiply on the left-hand side of both sides by A inverse if it exists. If we have a non-singular A, then we can find the A inverse. I multiply by A inverse on both sides. A inverse times A is the identity matrix. Identity matrix times X would just be X on the left-hand side. And then the right-hand side is just A inverse times B. Okay. I'll just do like one example of this because it's not that. Again, I like the RREF a little bit better. It's a little bit quicker. But every matrix equation is equivalent to a system of linear equations. And so if I have this system of linear equations, five X plus 10Y equals 25, and 7X plus 6Y is equal to 3. What I can do is I can turn it into a matrix equation in the following way. We take the coefficient matrix, which is 5, 10, 7, 6, times a variable matrix, which is xy. Notice I have to write the xy that way so that when I multiply 5, 10 times xy, it multiplies the correct way. And then set that equal to our constants. And again, I have to write it vertically there. If I call this matrix A or C or whatever I want to call it, let's call it A. This A is non-singular, so it does have an inverse. So it turns out the xy can also be found taking that A inverse and multiplying it by 25, 3. That makes sense? Now you have to be careful, you have to multiply on the left-hand side because of what we talked about earlier. Always multiply on the left. Otherwise, the dimensions don't work out. But this is just calculator work. We're going to do matrix A as a 2 by 2 matrix. 5, 10, 7, 6. And then I'm going to go into matrix, I'll call it B. This will be my constants, 25 and 3. Right? And then I just go back into my matrix menu, take A inverse times B. A inverse times B, and we get -3, 4. We've done this problem before, so That should have been what you'd expected. So we just did XY is that. So that means X is -3 and Y is 4. So you can solve systems of linear equations with inverse matrices as well, if you write out your system of linear equations as a matrix equation. Okay. And this can be done for any system of linear equations. I kind of like the RREF method a little bit better because then you don't have to adjust one matrix. You don't have to do as much calculations. You don't have to type in as much stuff. So I tend to use the RREF method if I'm solving systems of linear equations. I don't want to do it real quick. But this is another option. You can use matrix inverses as long as those inverses exist. Obviously, if this matrix is singular, then we can't use inverses to solve that. And that's another reason I kind of like RREF a little bit better, is because when you do an RREF, you immediately know whether you're in the no solution or infinitely many solution case. Because of that last row tells you what's going on. Here, if this is non-singular, then I don't know whether I'm in the infinite or no solution case immediately. I have to figure that out by doing other steps. Is that right? All right. Well, that is all. You can try another example if you'd like, or just look at the other example on your own, on the video that's posted. As a reminder, next week on Tuesday, what will happen, it will be an optional day. If you want to come in and ask me any questions about the test, any questions about the homework, I'll be available on Tuesday. I'll be in class, answer any questions. We can go over anything you missed out. I can talk a little bit about the test and what to expect. And then we won't have any class Thursday at all. All right. So I'll be around, but so Tuesday is optional. Thursday is like nothing, right? Because it's finals week. All right. If I don't see you next week, then have a good, make sure you're on your final. All the same stuff, you get 2 attempts. All that kind of good stuff. All right. I'll see you next, or I'll see you next week or not. Good luck.
Have a nice day.
Yeah, easy.